Hello, everyone. So today we would be discussing a paper which is on intermittent computing. Um, so, oops. Yep. So the name of the paper is a simpler, safer programming and execution model for intermittent systems. It's been worked upon by researchers from Carnegie Mellon and University of Washington. And the whole idea behind this paper is the development of a programming paradigm which kind of enables us to have better intermittent computing. So before diving directly into the paper, let's familiarize ourselves with some terminologies that might be useful during the course of the explanation. So the first being intermittent operation. So the very basic definition is that intermittent power is when the power is not continuous. So in a sense, intermittent operation refers to a process or system that operates with pauses or breaks in between periods of activity. So it's like instead of running continuously, now your program it runs for some time and then has periods of inactivity in between. So it's like on, off, and in such similar cycles. So the next term is energy harvesting. So energy harvesting is the process of capturing and converting various forms of energy from the surrounding environment into usable electrical energy. Now, this harvested energy can be stored or directly utilized to power electronic devices or systems. So, in a sense, harvested energy technologies are typically used in situations where traditional power sources like batteries or maybe power grid electricity are impractical or unavailable. The next thing is state persistence. Now, since the power supply is not continuous, your program execution is going to be halted as soon as it loses power. So, state persistence refers to the ability of a system or application to retain and remember its current state or data even after it has been shut down or restarted. So, in computing terms, state refers to the collection of data that represents the current condition or configuration of a program. Now, this includes variables, settings, registers, any interrupt settings, or any such information. The next is program consistency. So, program consistency refers to the property of a program to maintain a predictable and reliable behavior under varying conditions. So, a consistent program behaves in a manner that aligns with user expectations and system specifications, and it produces reliable results and it maintains data integrity. So, for a consistent program, you know what the output is going to be. You can predict its output. So, there are various different forms of consistency like functional, data, interface, behavioral, and so on. So, for us, program consistency is whether we get our desired output or not. Now, when it comes to all of this, we have quite a few options in the memory. I mean, we have quite a few different types of memory when it comes to using intermittents. Right now, till now, maybe when it's continuous power, we never think exactly of which memory do we need to store our program in. But when it comes to intermittent power and especially state persistence, the type of memory we use plays a very vital role. And for us, the RAM is kind of it's a temporary memory. SRAM gets SRAM gets wiped off as soon as you lose power, and it and when you start your power, your SRAM does not persist. So SRAM is not a good option to use here. ROM is a persistent permanent memory, but ROM is extremely slow. So you need something which possesses the properties of ROM, but it's also fast as SRAM. And so we usually use flash, EEPROM, or FRAM. And these three are associated with different ways in which we use these memories to bring about intermittence. So especially FRAM is what's predominantly used because FRAM in production chips offers convenience, speed, durability, and energy characteristics which are closest to SRAM. So programmers can use memory mapped FRAM to store variables that will survive power failures. In the case of Flash, reading and writing to Flash is more complex than reading and writing to FRAM. So in most of the cases, FRAM is what's used for intermittence. Now, let's go let's go to the main paper idea. Um, and in this paper, the researchers discuss what they call DINO, which is death is not an option, which is a new programming and execution model that addresses persistence and consistency challenges. So in DINO's programming model, programmers insert task boundaries to subdivide long-running computations into meaningful shorter tasks, such as maybe let's say if you want to sample a sensor or manipulate an important buffer, then you split this big action into smaller actions and you specifically put task boundaries. So, and now tasks are dynamically formed spans of instructions between task boundaries. And this is something which the programmer decides. And then tasks have well-defined semantics. So let's say the program's state at a task boundary should be consistent with the completed execution of the task that precedes it. So in the way it needs to follow the specific paradigm. Now, to support this programming model, DINO's execution model uses judicious checkpointing and recovery that tracks volatile and non-volatile states. We would be discussing more on checkpoint later in the slides, but this approach is kind of different than the previous systems that involved tracking only the volatile state and permit consistency violations involving non-volatile state. So by executing all instructions in its tasks, DINO guarantees that intermittent execution behavior is equivalent to continuous execution behavior. And so this paper puts forth its three major contributions, which is two ways to model intermittence, which is namely concurrency and control flow. And then both of these models are used to kind of convince us how DINO enables the behavior of intermittent programming, which is very similar to that of, let's say, continuous programming. And I'd say a vital piece of this is those task boundaries, so which provide task-based programming and task atomic execution to avoid consistency violations under intermittent power. And then finally, the authors evaluate a working prototype of DINO, including a compiler and runtime system for embedded energy harvesting platform. And then we evaluate DINO on diverse real-time systems and show that it kind of guarantees efficiency. So now, before jumping right into how the architecture of DINO is, intermittent execution comes with certain key challenges. And these key challenges uh, are fundamental. These are unsolved challenges which kind of disturb the program consistency. Or let's say you're running a particular task and you lose power, so what you do after that. So a key difference between intermittent execution and continuous one is that reboot is not the end of an intermittent execution. In a continuous execution, your program's running, and let's say you can have a reboot task at the end of your program, but then you are continuously getting power before getting interrupted. But in intermittent computing, you kind of get interrupted even before you finish your program. So this rebooting has two important effects on execution. The first is the all volatile memory is cleared, so which is SRAM, and control returns to the entry point of main. So this is something which is different in intermittent programming, and this is what we want to specifically address. So if we look at this figure, then this uses an example to contrast intermittence with our conventional execution. So the key difference between an intermittent execution and a continuous one is again that reboot is not the end of an intermittent execution. Now, between reboots, instructions execute sequentially, as in a standard execution model. But a reboot may occur before, during, or after any instruction. And this is something which we kind of need to address here. So non-volatile state retains its contents across reboots, and periods of execution are on the order of a few hundred to a few thousand machine instructions, which are in line with the intermittence characteristics. So within this specific execution model, we focus on certain methods to conceptualize the DINO execution. So uh, part A of the program is what our source program is, and B is how it's going to run under a continuous execution, which runs the program to completion. But figure C, wherein you're kind of breaking the program, is your intermittence, or I would say that's when you're losing power to the program. So this time you're not executing the entire program at once. So in continuous execution, you start from main and you go all the way to the end. But in the intermittent execution, you start from main. Let's say you reach length is equal to R1, and then you lose power. System reboots. Now you again start at main, append R1 is equal to length. Let's say you again lose power. Again, you start at main, append R1. So this is something which should not be happening, because then your program will never ever be completed. And thus we have dynamic checkpoints, which is main, append, okay, checkpoint this stuff. Now, even if you lose power, you're going to resume from the previous checkpoint. And that is what is checkpointing in very crude terms. Now, let's come to the intermittent execution model before you go into DINO, because intermittent execution model is something which is kind of persistent across many research papers. So we know that after a reboot, execution resumes at the checkpoint. Now, we know that since we are using checkpointing, your execution will resume at a checkpoint rather than main. And that is exactly the core idea behind any intermittent execution model. So dynamic analysis kind of determines when to copy the execution context, like the registers and your volatile memory, to a reserved area in non-volatile memory. And this can be done by, there's many different ways to do this, maybe using timer or using ATC to measure your input voltage. And these are just some basic examples. But dynamic checkpointing enables progress and ensures correctness for programs that use only volatile state. But past work does not address two problems that are fundamental to intermittent execution model. So what DINO or this paper suggests is that checkpointing is insufficient. So the first problem which they state is that dynamic checkpoints are opaque and implicit. And the second problem is that despite its persistence, non-volatile memory does not necessarily remain consistent across reboots. Now, this can be due to memory corruption, or maybe you lose power exactly when you're writing stuff to non-volatile memory, because when the system's going to reboot, it's not exactly in your hands. And so the authors try to address these concerns in their paper. So first, they address periodic dynamic checkpointing. Then they say checkpointing isn't sufficient. And one of their arguments in this paper is they're trying to model intermittence as concurrency. So when we talk of intermittence as concurrency, let's say if we take this example, then each period executes the same code beginning at the most recent checkpoint. But if concurrent periods are scheduled, then your program is gonna kind of concurrently run the same line at the same time. And when the execution halts, it's gonna continue at the line wherein it lost power. So it's something like, let's say, P1 is running, you have R1 is equal to length, R1's incremented, you store R1 in length, and then you have a reboot. But let's say your process P1 is kind of running, and process P2 starts running concurrently. And that's so whenever you have a reboot, your process 2 starts, and then process 3 starts, and so on. So at first, one period, so P is kind of like period. So concurrent periods are scheduled. Then let's say at first, one period executes and all others are unscheduled. A reboot corresponds to the executing period being preempted, and a preempting period begins executing. So preempted periods never resume. Preempted periods are the periods which are not planned. So access to non-volatile memory in preempting and preempted are kind of concurrent. So in our case, the solid arrow highlights two unintuitive consequences of intermittent execution. So the second execution period, P2, preempts the first execution period, P1, after P1 completes the write to the non-volatile memory, so which is the variable len. Now, this causes something which we call a data race with P2's read of length. So concurrent accesses may form data races. A data race can be a pair of memory accesses, at least one of which is write, that are not happens before ordered. So it's kind of like you try to read from length before writing anything to length. And this is something which can happen in this case. So this is something which is kind of impossible in continuous execution. And racing accesses to non-volatile memory in intermittent execution can be problematic because a race leads to an unintuitive result. If preempted execution period modifies a non-volatile memory location, then a preempting execution period reads the same location and the preempting period's read precedes all of its writes to the location. So this race problem can be addressed by DINO's architecture or DINO's programming paradigm. The next way in which the authors kind of model intermittence is through control flow. So we know that reboot. So control flow is more like a control diagram. So which kind of redirects control from arbitrary failure point to some prior point. So in this case, this is kind of defined through what's called a CFG, which is a control flow graph. So we have our control flow graph, and then we have a data flow graph. It's kind of the same program that's also being used in the previous slides. But this time we kind of make a CFG because let's say reboots introduce edges in the CFG graph that are followed on the reboot. So we can say that CFG is kind of a graph where each node represents a static code point and is the set of explicit control flow edges in the program. So all of these like checkpoint, R1 is equal to length, etc., can be said as static code points. And let's say the CFG for this program, which is kind of shown in the figure with implicit failure-induced control flow edges. So the possible checkpoints are dotted boxes, and a failure-induced edge begins at each code point and targets each possible checkpoint. So enter append kind of, how we can say, enter append gives invokes a checkpoint. Then it goes to R1 is equal to length. It again invokes a checkpoint, and it goes to R1 is equal to R1 plus 1, and then it invokes a checkpoint. So every time it invokes a checkpoint, it kind of decides whether this checkpoint is a valid checkpoint or not. So now coming to another paradigm of intermittent execution model. So in our model, a sequence of actions is atomic if code outside the sequence, that is, code executing after a reboot, cannot observe its effects until all operations in the sequence complete. So such an atomic sequence should also be isolated. Let's say operations in the sequence can observe the results of operations in the sequence or initial values from the start of the sequence. What this means is that you're running a particular task before a task boundary. So anything which runs after a reboot cannot access what was done in the previous cycle of execution. So we consider so this is what we call consistency. So we consider the state of an intermittent execution as consistent if it corresponds to one produced by some continuous execution and inconsistent otherwise. So this may lead to atomicity violations. And atomic is something wherein no external factors affect what you have in your system. It's kind of like a box, and nothing outside the box can affect what's inside the box. So so we call a code atom. So this is how we get the two conditions, like nothing outside the box can affect what's inside the box, and the initial values from the start of the sequence should not change from anything which is kind of changing these values, but something which is not a part of that function. So these are like the two conditions which, if a particular code meets, then we call it as atomic. Next is idempotence. So a computation is idempotent if it can be repeatedly executed without producing a new result. So we say that an execution experiences an idempotence violation when non-idempotent computation is repeatedly executed, producing a new result each time. So an intermittent execution manifests an idempotence violation when it executes non-idempotent code, reboots, and resumes executing at a checkpoint and re-executes the non-idempotent code. So in short, if your code is giving you different outputs every time you run it, then it's not idempotent, and that's basically an idempotence violation, which is shunned upon in intermittent execution model. So now that we know how, in general, intermittent execution models work, we can kind of dive into what DINO is and what exactly do they propose in the architecture of DINO. So programmers place task boundaries in their code. This is like the basic idea of DINO. And at runtime, dynamic spans of instructions between task boundaries form tasks. So let's say you have a code of maybe 100 lines and your task boundaries, let's say after every 25 lines. I mean, technically, this is not how we place boundaries, but just for simplicity, anything between two task boundaries is considered as a task. And DINO's programming model assigns clear task atomic semantics to program to enable simple reasoning, both human and automatic, about data consistency and control flow. So DINO's execution model ensures that tasks are atomic and data are consistent at task boundaries. So DINO uses data flow analysis and compiler-aided task cost analysis to help programmers place task boundaries in a way that ensures consistency and minimizes overhead. So basically, DINO helps you identify where in your code you can place these task boundaries such that your code does not violate any atomicity violations, any idempotence violations, and at the same time, it kind of satisfies the control flow and the data flow in your program. So this was more like what the idea is. Now, coming to the programming model. So DINO's programming model assumes a C-like base language because C is kind of synonymous with embedded development, though it does not depend on language features that are unique to C. But DINO adds several features to the base programming language. So coming to diving further into what exactly DINO does is DINO adds task semantics to C's programming model. Now, the programmer statically defines task boundaries at code points where they expect data consistency. So there should, in this case, there is some input which is kind of required from the programmer. But conceptually, programmers should think of task boundaries like memory fences that are meaningful at compile time, rather than thinking of tasks as, let's say, statically defined regions that happen to have uh, delimiting boundaries, because task boundaries are defined statically while tasks are formed dynamically. So, as with a memory fence in concurrent programs, programmers must be careful to kind of include sufficient task boundaries to provide the atomicity and consistency required by their application. And so, this is something like if we see this figure, then it shows, so the figure 6a, there is the void main s is equal to rd sensor, and then we have a DINO task. This DINO task is exactly what's kind of storing data, or it's kind of defined, it's a task boundary. And the compiler or DINO suggests you where to put this task boundary. So this figure shows part of an activity recognition program, which is like one of the benchmark for assessing DINO's capabilities. But this program in the A part is decorated with task boundaries and slightly modified. So the figure shows statically placed boundaries in line with program code. Now, the B part shows how a task is dynamically defined during an execution as a path from one task boundary to the next. So you have each task is like a path between boundaries, and the numbering is how the tasks flow, but during DINO. So in the figure, one task, let's say, spans from operation 6 to operation 4, including code on just one side of a branch, and then return from the UPD STATS, like the C thing. So it kind of runs from 6 to 4. And then, so A shows you static task boundaries, B shows tasks which are formed dynamically from these boundaries, and C shows how task boundaries are failure-induced control flow targets in a control flow graph. So technically, C is the same representation as B, but this time it's in the form of a control flow graph. And UPT stats is what's exactly how we can say the result of this program. And V shows how your tasks are kind of getting executed with DINO. So jumping into the execution model, there are two important things which we kind of need to understand here. The first is checkpointing, which we already have a crude idea of, and data versioning, which kind of keeps data consistent despite reboots. So coming to checkpointing, it's something that's done at every task boundary, and a checkpointing mechanism in DINO runtime copies the registers and the stack to a linker reserved area in non-volatile memory, which is usually FRAM. So state preservation across reboots is necessary to ensure progress. So again, at every task boundary, a checkpoint in the DINO copies this important data to non-volatile memory. And these checkpoints are double buffered so that newly written checkpoints supersede prior ones only after being completely written. This was something which we discussed in one of the previous slides, wherein if you're writing something to a buffer and you lose power, then that buffer is kind of like corrupted, or that's an inconsistent buffer. So you need to discard it. And that's why we have a double buffer mechanism so that newly written checkpoints kind of overwrite the previous ones only after they are completely written. And to protect against failures during checkpoint, the final operation of a checkpoint is to write um let's say a fake value that must be intact, not a fake value, it's kind of like a dummy value that must be intact for a checkpoint to be considered restorable. This is something like a flag or a Boolean flag or something. So in contrast to dynamic checkpointing, which was described, DINO takes checkpoints only at statically placed explicit task boundaries. So capturing execution context in a non-volatile checkpoint at each task boundary ensures that volatile data are consistent across reboots. Now coming to data versioning is something that ensures that all non-volatile data remains consistent across reboots. Checkpointing ensured, oh, sorry. Checkpointing ensured that your program is going to execute at the same line after it loses power, and data versioning is what makes sure that the data that was previously, let's say, calculated is not lost or is persistent even after you resume power. So a mechanism ensures that non-volatile data remains consistent across reboots. And DINO's execution model ensures that at task boundaries, non-volatile data are both internally consistent and consistent with the task boundaries checkpoint of volatile state. So let's say when the execution reaches a task boundary, then immediately before checkpointing, DINO makes a volatile copy of each non-volatile variable that is potentially inconsistent. That is, something that may be written non-idempotently after a task boundary executes and before another task boundary executes. So it's something that can be possibly be corrupted during the whole I can say during the whole checkpointing process. So that is something whose copy is made And so copying this non-volatile variable to volatile memory on the stack ensures that checkpoints include these variable values. So DINO's implementation of task boundaries includes corresponding code to restore non-volatile variables from their checkpointed volatile versions when the execution resumes. So this is something which happens before checkpointing. And in this way, you ensure data consistency across reboots. Now, coming again to control and data flow graphs. So DINO's versioning and checkpoint prevents atomicity violations and idempotence violations by design. How? We discussed about the data versioning and the checkpointing. Now, DINO uses statically defined task boundaries. So this addresses high control flow complexity of systems that dynamically collect checkpoints. So in that sense, a key advantage of DINO is that target of each failure-induced control flow edge is statically known. So you know when the program is going to lose power. But so you place the task boundary as per when you know that the model is going to lose power. But with dynamic checkpointing, there is a control flow graph edge from each point in the program where a reboot can occur. So it's kind of difficult to determine where you should place your boundaries with dynamic checkpoint. But with Dino, there is an edge from each point where a reboot can occur to only those task boundaries that reach the point in the graph. So you kind of model where your execution is going to go. And that is exactly what this control flow graph is. And with Dino, this edge can only point to another uh, task. So in 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 a non-Dino environment, you might have multiple outputs going away from a node, but with Dino, you only have outputs that are going to other task boundaries. And task boundaries are definitely lesser than the number of lines which you have in your code. So in that sense, Dino's task atomicity eliminates the failure-induced non-volatile data flow suffered by intermittent executions. And these edges are eliminated because tasks are atomic and isolated. So Dino's simpler control flow and absence of failure-induced data flow simplifies reasoning about failures. But then again, we need to have some feedback on task boundary placement because task boundaries introduce checkpointing and versioning overheads. Naturally, these things are not required in a continuous program. But in intermittent programming, you have an additional task of writing this to a non-volatile memory, and that in itself requires some energy and takes some overhead. So Dino requires programmers to manually place task boundaries, which make implicit control flow explicit. But it also suggests that programmers think about cost of tasks in two ways, like a task boundary overhead and a failure recovery cost. So Dino exposes these costs with compiler warnings, and this is something which they stated is a change they make to some fundamental things in C. That is, now task boundaries introduce checkpointing and versioning overheads, but the checkpointing overheads increase with the size of the stack and versioning overhead increases with the size of non-volatile data accessed in a task. So Dino's compiler emits a warning for each boundary that can be moved to a point of lower cost, example where the stack is smaller. And then again, the second cost dimension is that failures of actions such as IO actions may be expensive to repair. So making such tasks very short and minimizing unrelated actions minimizes this risk. So Dino's compiler emits a warning when a task includes access to a peripheral register indicating likely non-idempotent hardware use. Now, this might be either an input from an ADC or an input from a button or audio input or anything. This suggests that programmers try to construct task boundaries as close as possible around this access. And so all of this is just an effort to make the program as idempotent as possible. Now, this was the whole idea. Let's come to how exactly Dino is implemented. So we talked about Dino giving you warnings. We talked about Dino please have we talked about DINO in terms of placing task boundaries, but what exactly is it? So DINO has two components. It has a compiler that analyzes programs and inserts DINO's runtime code, and a runtime system that directly implements the DINO execution model, including checkpointing, data versioning, and recovery. So we can say that if we first look into compiler, so the DINO compiler is a series of passes for the LLVM compiler framework. So the DINO compiler uses data flow analysis to identify potentially inconsistent data that must be versioned at a task boundary. How it does this? It does this with the control flow graph. Now it translates programmer-defined task boundaries into calls into the DINO runtime library. And then it analyzes task boundary placement and suggests changes to reduce runtime and checkpointing cost. So in that sense, the compiler determines for each task boundary which potentially inconsistent variables must be versioned to provide consistency upon resumption. So if we say then, mathematically speaking, then for each non-volatile store, let's say S to a location LS, the analysis searches backwards along all control flow paths until it hits a most recent task boundary on each path. Now, since we've already established that DINO tasks are atomic, then the analysis of each path can stop when it finds a task boundary. So in that sense, the prototype assumes that no non-volatile accesses are happening before the program's first task boundary. And these task boundaries are points at which execution might resume if a reboot follows the non-volatile store, which we initially defined S. So it doesn't follow S's execution. I mean, this is kind of difficult to understand at first, but this just means that oh, you kind of know what variable was returned to the volatile memory if you travel the control flow graph and you hit the most recent DINO task. And that, if you hit the most recent DINO task, then you kind of get a whole you kind of get a whole log, not a log file, it's kind of wrong, but you kind of get an information as to what stuff was stored in the non-volatile memory. Now the programmer inserts task boundaries, which are also called the DINO task. Now encountering such a call, the DINO compiler first determines the set of non-volatile variables to version using the analysis in the in what we discussed in data versioning. But then it then replaces the call to DINO task with calls into DINO's runtime library that version the relevant non-volatile state, which is the DINO version, and checkpoint volatile state, which is DINO checkpoint. So the program is linked to DINO's runtime library that implements these functions. So those are like the key functions of this compiler. So that is identifying potentially inconsistent data, and that we do with LLVM passes, compiling task boundaries, and then analyzing the task cost. Now we also have DINO's runtime. So DINO's runtime system is what implements the checkpointing and versioning required by its execution model. So let's say when the program begins in main, it first executes a call to restore state. Now this is automatically inserted by the DINO compiler. Now this runtime library function copies the data in the current checkpoint back into the original corresponding registers and memory locations, saving the program counter, stack pointer, and frame pointer for last. So the function copies the versioned non-volatile variables in the checkpoint back into their original non-volatile memory locations. And after restoring volatile and non-volatile data, the function restores instruction pointer, stack pointer, and frame pointer, redirecting control to the point where DINO collected the checkpoint, and from there, execution continues. So it's like you have restore state, and restore state just takes all the data from your wallet. It kind of halts the program, takes data from your volatile memory, stores it exactly at those places wherein it needs for the program to run as if it's continuous execution. And once all of that is done, it moves the instruction pointer, stack pointer, and frame pointer back to your main function, and your main function executes till the time it hits another DINO task. And so this was like the whole execution of DINO. And in order to test DINO, we need some applications and benchmarks. So in this paper, the authors have used three benchmarks. So the first is a machine learning based activity recognition system, which they took from a previous published work, and they run this on intermittently powered WISP hardware platform, which is kind of called WISP. So the WISP harvests radio frequency with a dipole PCB antenna that charges a small capacitor via charge pump. So the WISP has an analog device's low power accelerometer connected to an MSP430 FRAM board via SPI. So AR, which is the program, maintains a time series of three-dimensional accelerometer values and converts them to two features, mean and standard deviation vector magnitude. And it uses a variant of nearest neighbor classifier to distinguish shaking from resting. So AR counts total and per class classifications in non-volatile memory, and each experiment collects and classifies samples until the total count of classification reaches 10,000. Then it terminates lighting an LED. So, I mean, if we just ignore what exactly AR does, in short, it just takes 10,000 readings. And once it takes these 10,000 readings, the program terminates and it lights an LED. And they try to run this on intermittent power, which is something very similar to running an encryption algorithm on intermittent power. Now, the second program is a data summarization application on a TI project board with the same MSP430 FR microcontroller. They connected the board to a PowerCast power harvester, energy harvester board, and a half wavelength wire antenna, all mounted on the breadboard. Now, what DS does is it summarizes data as key value histogram, in which each key maps to a frequency value. One function adds a new data sample to the histogram by locating and incrementing the corresponding bin. Another function sorts the histogram by value using insertion sort. So the test harness for DS inserts random values, counting 2000 insertions with a non-volatile counter and sorting after every 20 insertions. So the sorting routine swaps histogram keys using a volatile temporary variable. And if a swap is interrupted before the key in the temporary, then it's reinserted, that the key is lost from the histogram and two bins end up with the same key. So the structural invariant for DS, which kind of test harnesses the checks after each sorting step, is that each key should exactly appear once in the histogram. And if that check fails, then the histogram is in inconsistent state and DS halts, illuminating an LED to indicate the error state. So this is like you are taking values, and then after every 20 insertions, you're doing an insertion sort. So both of these programs kind of had the same paradigm, that they were essentially counting programs. And then the third program is a radial MIDI, which is musical instrument digital interface, which they connected to a project board. Which was kind of hosted on a project board, and they connected this board to a peppermill power front end that harvests mechanical power of a manually rotated DC motor for use by the project board. Now, MIDI, like the program, generates batches of note on messages with a fixed pitch and velocity proportional to the motor's speed. It stores messages in a circular list data structure and tracks the index of the message being assembled, incrementing the index to store each new message. When all entries are populated, MI copies the messages to a separate memory region, clears the old messages, and resets the index. So a power failure in this case can trigger an idempotence violation that increments the index multiple times, eventually leaving it referring to a non-existent entry. So MI checks that the index is in bounds before using the buffer and aborts with an error LED if it is not. So in each experiment, MI generated messages in batch of 4, and it terminates after 10,000 messages. So again, this is something essentially also a counting algorithm. And so as per, so the crude, not the crude, but a basic evaluation of this is given in one of their tables in the paper. And so the data count failing X and non-failing X trials with and without DINO for the MI and for the DS at 60 centimeter, it's taken at 60 centimeter and the error at 40 centimeter for AR. So essentially you need to have, it's since all three of these are kind of wireless, you need to also calculate the distance, and that distance kind of defines how long you will have your positive cycle. Now, again, reboots and time overheads are not meaningful for MI, since MI kind of is a reactive program rather than um, a counting program. I mean, it's essentially a counting program, but its output depends on its input. So you have the error percentage, which is the baseline percentage, and baseline is in the absence of DINO. And then you have its configuration with DINO. So the first column just states simple error. The second column of table 2, like this table, shows the error AR experiences with and without DINO at 40 centimeter from the RF power. And so AR sees no error with DINO, but it suffers nearly 7% error without DINO. And so column 2 and column 3 just give you the number of reboots and then the overhead. Essentially, DINO has a higher overhead because we are checkpointing and data versioning, but that kind of promises a 0% error. Columns 4 and 5 show failure data for DS running with and without DINO at 60 centimeters from the RF power. So DS does not fail with DINO. You can see that it's essentially zero failure and all 11 test cases pass. But a test confirms the difference in failure rate is significant. So DS experiences no failures with DINO, but about 5.5 times as many reboots, because the number of reboots with baseline is 13.4, but the number of reboots with DINO is kind of like 72.5, which is kind of logical because with the overheads, your program length has increased. So now it requires more reboots to execute the program. And essentially, since the number of reboots is more, the number of tasks to be done, which DINO has put in are more, your overhead is more. But all of this is acceptable because we have absolutely zero error. And the last two columns show failure data for MI with and without DINO. Again, this is impressive because MI absolutely does not fail with DINO, but it fails all the time during its baseline. So DINO fails 100% of the, sorry, MI fails 100% of the time without DINO, and it processes just 975 messages on average before failing. So MI kind of reveals an important feature of DINO, which is like naively porting code to an intermittent context threatens functionality. But with DINO, failure-free porting requires placing just a few task boundaries. And these are more like the evaluation graphs. So there are two main sources of runtime overhead. The first is checkpointing and versioning data. And this extra work costs cycles and hence it leads to more reboots. And that was something which we discussed in the previous slide as well. Now under RF harvesting, AR without DINO experiences reboots, which is this one, the first graph. But error bar represents standard error and the bottom plot shows analytical and available power. So the last graph is how much power is available at what distance, since it's an RF antenna. The second graph shows you the percentage of error, and the first graph tells you the number of reboots it did. And all of this data is calculated with respect to the first benchmark, which was the activity recognition. And then again, the last graph is something which has to do with control data flow. So this shows a CDF of points where execution may resume after a reboot for all instructions in all the three benchmarks. So you can see that for DINO, The number of points where execution might resume is small, never more than 4, and in most cases just 2. Whereas for dynamic checkpointing like Mementos, which was a previous paper, the number is much higher. And this was what we discussed in one of the previous slides, wherein in your control flow graph, your outward arrows, like where your program will go from before a particular reboot, is now defined by DINO tasks rather than, let's say, any arbitrary point in the program. And that's why your program has does not have any atomicity violations now. And this graph kind of proves that, because again, with DINO, the maximum number of points it might resume is never more than 4. And then coming to the result statements. So the first important result is that DINO enforces consistency. We saw that in whether it be MI or it be DS or it be AR, your error is extremely small. In fact, in MI, your error is 0. Again, in DS, your error is 0. Your error is 0 in AR too. So DINO enforces consistency. But at the same time, DINO imposes reasonable overheads. Again, going back to that, your overhead was 1.8 times in AR and 2.7 times in DS. So at the expense of consistency, DINO is also imposing some overheads on your program. A DINO reduces control complexity. This can be said by this last graph, wherein the number of points wherein your program can hop to is extremely small. So your control complexity now reduces with DINO. And the fourth being DINO helps place task boundaries, because DINO's compiler sends you warnings wherein you have unnecessarily placed tasks. So it kind of aids you or helps you to place task boundaries. So these four are like the main statements of DINO. And this is what the whole paradigm of DINO rests upon. And so the other related works which are similar to DINO are maybe pertaining to whole system persistence, which uses a capacitance-backed volatile memory to provide flush on failed semantics to an entire operating systems. Even DINO provides persistence for arbitrary data, but it does so without any additional hardware. We have another papers which are quick recall and Mementos, which kind of aim to make computational RFIDs viable for general purpose applications. But both dynamical checkpointing volatile data to non-volatile memory, preserving it across failures. Now, unlike DINO, neither of these systems address inconsistencies in non-volatile memory. Also, both Mementos and Quick Recall kind of dynamically decide when to checkpoint heuristically at loopback edges and function returns. So by contrast, DINO checkpoints at each programmer-defined task boundaries. And so DINO has fewer failure recovery targets. There's another thing called, there's another thing called eidetic. Eidetics are checkpoints in ASICs that operate intermittently, and it optimizes checkpoint placement and frequency of checkpointing at runtime based on energy conditions. Then there is something called PMFS, which is similar to persistent memory write barrier and implements a file system for block persistent memory. Another related work is NV heaps, which considers the safety of memory mapped non-volatile heaps, focusing on pointer integrity, and provides a programming construct for non-volatile transactions. Now, DINO's task atomicity could be implemented along with NV heaps generational locks, but DINO's operation is fundamentally different from heap management, since again, embedded systems generally avoid dynamic allocation. And the last related work is Kiln, which adds non-volatile cache to the memory hierarchy to speed up persistent memory with in-place updates to large data structures that persist in cache until they're flushed to backing storage. So these were like some of the related works along with DINO. And so some applications that work on consistently part devices may execute surprising failure modes, but when they run on intermittent power, they can offer other inconsistencies. So as energy harvesting becomes a viable way to power computing platforms, with next generational non-volatile memory, ensuring data consistency under intermittent power will be crucial. And that is exactly where DINO plays a big part, because DINO simplifies programming intermittently powered applications by reducing complexity, reasoning failures, and actually enforcing data consistency. And so in that sense, DINO lays the basic groundwork that can serve as a basis for future work on programming and system stack for intermittently executing devices. So that was the future work which they have kind of proposed in DINO. But then this was all about DINO, which was a paradigm for intermittent computing. So this was all in the explanation for this paper. Thank you so much.